Hello, I hope you can all hear me. I would first like to thank the organizers for giving me the opportunity to contribute to this meeting. Thank you very much. I will talk on the characteristic cohomology or topics around characteristic cohomology. And I suppose from the schedule that I have 45 minutes, please correct me if I'm mistaken on that. So thank you very much, and let's start. I hope you can see my screen here.
Yes.
So the aim of this talk is to report on one of my recent preprints, which is called On the Topology of Determinantal Links, and it can be found on the archive under this identifier. And what I also want to emphasize in this talk is how it relates to the work of Jim Damon, characteristic cohomology 1 and 2. I also put the archive identifiers here. I think the first paper has already been published. I'm not sure about the second, but the reference for the first can also be found in the end of this talk. So let's briefly discuss the principal setup that we're considering. And it's a setup introduced also by James Damon. And it's what he calls a singularity of type Y. So what we do have is a map capital F, holomorphic map germ from CP to some Cn. And then in the target space, there's another variety Y. And then what we consider is the preimage of this particular variety or singularity, and I call it X with F in the index to indicate the role of the map F here. So it's the preimage of this model singularity Y on the right-hand side. And what you usually do is, in this setting, you impose certain transversality conditions on this map F relative to this singularity Y, which could, for example, be, first of all, maybe you want to have expected codimension for this singularity XF. Expected codimension meaning that the codimension of XF in CP is the same as the codimension of Y in Cn. Then maybe you want to impose stratified transversality, or another notion that is also discussed in James Damon's papers is logarithmic transversality and so on. So to give you an idea of what this might look like, I brought some pictures, or I tried to draw some pictures. What you see here on the right-hand side is the model singularity Y, which is in black, and I chose a Whitney umbrella that you might be familiar with. And on the other left-hand side, we have CP with P equal to 2, so a plane, and then a map F, which embeds this on the other side as a cuspidal edge. This is just an example, and then you see the intersection of the image of F with this model singularity Y, and you consider the pre-image, which can be found in red on the left-hand side here. So this is the general setup. And then in this setup, one has usually different notions of deformations for this singularity XF. The first deformation, or the first set of deformations, which is much discussed by James Damon, is when the model singularity Y has deformations itself. For example, when it is a hypersurface given by one polynomial or holomorphic equation F. In this case, you have a smoothing of the model singularity. It has a Milnor fiber. I denote it by MF over here, right? So now the Whitney umbrella has been smoothed out. There are no singularities of this black object anymore. But the map capital F here, this map has stayed untouched, right? It's still the embedding of the cuspidal edge. And in this case, nevertheless, the preimage of this smoothened y is now also smooth, right? It's again here in red on the left-hand side. I try to give you an idea of the pre-image of y. So the other deformations that you're given is you fix the model singularity y, but you vary the map capital F, right? So you consider an unfolding of this map capital F, and you unfold it. In this case, the cuspidal edge becomes a nodal surface, or the product of here a nodal cubic with a line, right? So you perturb it in a more or less generic way, if you wish, and then you can still consider the pre-image of the model singularity y, and you find this pre-image here on the left-hand side. And one thing you observe, or you can observe, is that when the model singularity y has non-isolated singularities, as is the case in this picture for the Whitney umbrella, then these singularities can usually also be seen on the other side. I try to draw this with the green dot. It lies on the one-dimensional singular locus of the Whitney umbrella, and it induces a singularity of this deformed fiber of XF. So, what is characteristic cohomology? James Damon introduces these various different notions. So the first notion is for the case of a hypersurface, when the model singularity is a hypersurface, and what you have then is the map capital F is a map of Milnor fibers, right? On the right-hand side, you have the Milnor fiber of your model singularity. On the left-hand side, you have the Milnor fiber of the XF. And of course, this map induces a pullback in cohomology. And then the definition that James Damon gives is the characteristic cohomology is just the image of the pullback in cohomology from the Milnor fiber of the model singularity. So there's a universal object, and you pull back the cohomology from that. And that's pretty similar to characteristic classes of vector bundles and classifying spaces, or not pretty similar, but this is a parallelism that James Damon alludes to, and this might be a convenient way to think of this or to motivate this. So what's the next notions of characteristic cohomology? Well, in the general case, you can also consider no deformations at all, but just suitable representatives of, or a suitable representative of your map capital F from some sufficiently small balls. Then by definition, you have these inclusions of some representatives of the model singularity y and the XF on the other side. But you also have natural inclusions of their complements, right? So another definition of characteristic cohomology, namely the characteristic cohomology of the complement, is given by the direct limit of these relative homology groups of the complements, where I have to say that this is not exactly the definition that James Damon gives. He's considering some limit of the complement itself, but up to a shift, these notions should be equivalent. So, yet another definition of characteristic cohomology that he gives is the cohomology of the link. But maybe let's go ahead yet. The idea you should take is something universal from the model singularity gets pulled back in cohomology to the singularity XF. All right, so one particular setup that that falls into this category of singularities of type Y is determinantal singularities. And some of you may know this is one of my workhorses. So let me briefly recall what a determinantal singularity is. In this case, the model singularity Y is just given by the space of matrices with a bound on the rank. Some space of matrices you choose, M by N, and then you have a bound on the rank, S, and you take this singularity. Then by construction, this map capital F is given by a matrix with holomorphic entries, holomorphic in some variables x1 to xp, and then the other singularity on the left-hand side is just the preimage of this degeneracy locus, of this set of degenerate matrices. And then we say that this is a determinantal singularity if there's this algebraic transversality condition to have expected codimension, right? And we say that it is an essentially isolated determinantal singularity. This is a notion introduced by Wolfgang Eberling and Xavier Hussein-Zadeh. If this map A is transverse to the rank stratification of the generic determinantal varieties. The rank stratification is a Whitney stratification of this space of matrices, which is just every stratum consists of the matrix of the set of matrices of a specific rank R, right? And the map A has to be transverse to this stratification. So why is this interesting, or why is this accessible to considerations of for characteristic cohomology? Well, in the case of square matrices and just the set of matrices with vanishing determinant, we have a hypersurface, and then the Milnor fiber of, or the smoothing of this model singularity is well known. We have a quasi-homogeneous, even homogeneous singularity, so we don't need to care about the size of Milnor balls. We can take the whole affine variety as a representative, and the Milnor fiber is nothing but the space of matrices with determinant 1. And then, you know, this is the special linear group, and you even know that this has a well-known cohomology. Namely, the cohomology ring of this variety is isomorphic to the exterior algebra on some set of generators of odd degree, starting from degree 3 and then going up to degree 2n or 2m minus 1. So it has the cohomology of a product of spheres, but it is not a product of spheres, right? It has only the cohomology. So a very accessible model for the cohomology from which you pull back. And the same holds for the complement of the generic determinantal varieties, even in the non-square case, where you know that this is a Stiefel, or it has the homotopy type of a Stiefel manifold, and it's again an exterior algebra in some odd generators. So for non-square matrices, the generic determinantal varieties, that is the model singularities, are rigid. That means you have no way to associate a Milnor fiber to this model singularity. So this, what you saw as an example in the hypersurface case, this cannot happen. But what can happen is this second picture that I tried to draw. You can only deform the map capital F, but the model singularity Y stays untouched. So for non-square matrices, the generic determinantal varieties, what you saw in this picture here is, or when you look at this picture here, you can ask the question, when do I even have a chance to obtain a smoothing of my XF just by deforming this map capital F, right? And what you can maybe already expect from the picture is you have to move the image of F away from the singular locus of Y. And this is merely a condition on the dimension of the source versus the codimension of the singular locus in the image, right? So the question is, do you have this green dot or can you avoid it? And it's a dimension count. Here's the statement. This is smoothable, or a determinantal singularity XS A in CP, which is given by some matrix, some m by n matrix A. is smoothable via an unfolding of A if and only if this P is smaller than the singular locus of the generic determinantal variety in question. So if this happens, you can do this perturbation, and then the smoothing of your singularity XF appears as the preimage of a single stratum under a transverse map. Right? So I try to draw another picture because I cannot draw a expected code. Now, the other picture with the Whitney umbrella was not so well suited to illustrate this, so I passed to another model singularity. Here you see why the model singularity is just a cone with singular locus of dimension 0 here. And in this case, you can move the image of a two-dimensional map. You can move it away from the singular locus, right? So you have a transverse intersection for a generic map here. And on this side, you see the preimage of these transverse intersections. So the basic question is, the basic question that I'm asking is, what is the pullback in cohomology from this particular stratum, right? James Damon takes the Milnor fiber of the model singularity and pulls back from there. What I do is I take the one stratum that is being touched by the perturbed map, and then I pull back from that stratum. And of course, I have to motivate this question and see that it makes sense and there are results which are reasonable. And this is what I will spend the rest of my talk on. Plus, I also want to address the question, how does this fit in the picture with the various notions of characteristic cohomology that were defined by Damon and that I briefly discussed before. For example, he's having some discussion in his papers that the cohomology of in the hypersurface case again, that here the cohomology of the induced smoothing of XF, right, it splits as the characteristic cohomology and then some other summand which is concentrated in cohomological degree equal to the dimension of this Milnor fiber, right? And this direct summing decomposition can be observed in two cases, or in two extremal cases. One is where the matrix A is the map of a submersion, and the other case is when this dimension of the source P is less than the codimension of the singular locus, right? Which is also the case in my setup. So this is something he observes, and the mu is the singular Milnor number of the singularity. It's a notion that is introduced elsewhere. But the thing is that James Damon raises the question, how must this formula be modified for general singularities of given type, right? And I want to propose a partial answer to this question. Okay, maybe I can ask whether somebody has some questions so far. I hope there have not been technical difficulties up to now. If yes, then please let me know. And
okay.
Are there questions? Okay.
No, there are no.
All right. Then let me go on. So we saw earlier that the cohomology of the model singularities in the hypersurface case and of the complement in the general case, these cohomologies are very well known. And first thing that I want to start my observations with is that these strata from which I want to pull back, they also have a pretty nice cohomology. And this cohomology can be described by by studying the natural Lie group action on the space of matrices. You have the Lie group GLM times GLN, and action by multiplication from the left and the right. And then these strata appear as orbits under this Lie group action, right? So you, for instance, you take this matrix which has unit matrix of rank R in the upper left corner and elsewhere zeros, and then every matrix of rank R, specifically R, can be reached by left and right multiplication with some P and Q. And one thing I discuss in my paper is that the cohomology of this orbit is graded isomorphic to this tensor product of the cohomology of the Grassmannian of R planes and M space with the cohomology of this Stiefel manifold, right? And the cohomology of this Stiefel manifold we saw before already in the work of Damon. It's an exterior algebra in a free module on odd generators, or in generators of odd degree. And the cohomology of the Grassmannian, on the other hand, is also a rather well-known object, which nevertheless can be quite complicated. But it's generated by the Chern classes of the tautological bundle, right? So for the Grassmannian, everything lives in even degree. And you even get back the cohomology of the complement of the generic determinantal variety if you set R equal to M. Then you have here the Grassmannian of M planes in M space, which is just a point. And here you have the Stiefel manifold that you saw earlier. So this is a generalization of what was already mentioned in James Damon's papers. But one thing that I should warn you about is, even though the right-hand side looks like the cohomology of a product of this Grassmannian with the Stiefel manifold, it's again not the case that there's any map from this product to the orbit which induces this isomorphism in cohomology, right? So you should be very careful about this and keep in mind this is just an isomorphism as graded commutative algebras. Okay, let's go on. What I study in my paper is real and complex links of higher codimension. And this is another notion that I need to introduce, but it's not too far away from this singularities of type Y. It's in fact, it is one other instance of this singularities of type Y. So what is it? We have model singularity Y again, and then you could say you just take linear maps to this target space or linear sections of this model singularity, right? And if you take hyperplanes DI, you intersect your model singularity with these hyperplanes, then you will again obtain a singularity, and I say the real and complex links of codimension I are the respective real and complex links of this generic hyperplane section. And what should be immediate from the definition is, if you don't choose a hyperplane at all, you just have the classical notions of real and complex links, right? This is the intersection with a sufficiently small sphere, and the other one is intersection with a ball and a codimension 1 hyperplane in general position of the origin. And this is what I mentioned before. You can think of these complex links, you can think of as Milnor fibers of a singularity of type Y for the embedding of this hyperplane. And the deformations of this. So it fits very well within the framework that we discussed before, only that the map F, the map capital F, has to be linear. And why do we consider these spaces? Well, in some years ago, I showed that whenever you have an essentially isolated determinantal singularity, which is defined by some matrix A, then these complex links of higher codimension, they play the role of some fundamental building blocks for this smoothing of the, or for the essential smoothing of the determinantal singularity. Where do they appear? Well, here, this is the complex link of the generic determinantal variety of M by N matrices with the bound S on the rank. And this last term is the codimension that I want to consider. Right? So this is a term that always appears in the Milnor fibers. And then here you have a suspension or a double suspension. This is the multiplicity of the double suspension. And here again, this is the complex link of the generic determinantal variety, but along this particular stratum. And R is the index which runs over all strata in question. And then here's another sum which runs with some index from I to some number lambda. And this lambda is, it comes out of the Bouquet Decomposition by Mihai Tibar, which I built on. And it can be seen as some kind of Milnor number for this determinantal singularity in a certain sense. So that's why the real and complex links, or the complex links in particular of higher codimension, are important to me. And whenever this determinantal singularity XS A admits a smoothing, which comes from a perturbation of the matrix, then this whole term simplifies in the sense that this wedge sum disappears. There's only one stratum in question, and you just have one lambda here, and the term becomes this simple. And already here, you see some similarity with the question raised by James Damon, right? So this could play the role of the characteristic cohomology, and this could play the role of the term with the Milnor number. And we'll see that this is not 100% the case, but we'll get back to that. All right, so real and complex links of higher codimension, they are supposed to contribute my proposal for characteristic cohomology. And what we can, so we should look into their properties. And what we can say is these generic hyperplanes, these generic hyperplane sections of our model singularity, they can be chosen inductively, right? So they are all generic hyperplanes. We can first choose one of codimension 1 here. Then we choose another linear form which cuts out the next one. And we go on and we go on as much as we like until we reach something of codimension I. And then what we can observe is that by genericity of this DI, of these hyperplanes, these spaces, these intersections are again Whitney stratified just by intersecting the strata which are already there, intersecting them with the generic hyperplanes. And one thing you should keep in mind is once this codimension I is sufficiently big, then this intersection will have isolated singularity, right? Think of the Whitney umbrella, or maybe the Whitney. No, the problem is it's a little bit difficult to draw pictures of this anymore. But think of a space with non-isolated singularities in place of Y. You have generically the hyperplane sections will also have non-isolated singularities, but if you cut down sufficiently often, then eventually you will reach a point where you have isolated singularity in the Y, or Y intersected with this hyperplane, and then the associated real and complex links are smooth, right? So here I wrote the codimension I complex link of this singularity Y, which you can you can define as here Milnor ball, here the generic hyperplane, and then you need one additional linear form and a regular value of this linear form on that stratified space, which is a regular value sufficiently close to the origin. And then you get a smooth space. So what we can do is we can track the maps in cohomology from the inclusion of these real and complex links. And we have to be a little bit careful about what these inclusions mean. So K0, the codimension 0 real link is just the classical real link of Y, so intersection of Milnor sphere with Y. And then in there, you can think of the complex link as sitting in the real link, but of course you have to do this Milnor deflation to the side a little, right? So this, I hope this is known to the experts. Anyone else, feel free to or look at the original source by Milnor. Goreski McPherson's book on stratified Morse theory also has some sections on it, and also very nice illustrations. So details can be found there. But we can consider the complex link as a subspace of the real link, and then the complex link as a boundary, which is the real link, or which is diffeomorphic or homeomorphic if you have stratified setting, homeomorphic to the real link of codimension 1. And then this goes down and down and down as far as you wish. You go until some codimension I that you want to study. And because everything is stratified, you can also study what happens only to the regular loci. Right? So here you have the smooth locus of the real link of codimension 0, the smooth locus of the complex link, and then their hyperplane sections, their generic hyperplane sections, and you can go down and go down and down and down. And this might be something that you don't get the idea to study this because these are not closed embedded closely. No, these are manifolds which are not closed embedded manifolds of your ambient space, but only locally closed embedded. But I observed the following lemma, or what I put in the lemma here. The following miracle to me still is that the maps in cohomology from this cascade of inclusions up there, it's an isomorphism in all degrees below the middle degree, right? And in the middle degree, it is injective. And now this is only for the regular loci. And okay, but I should say you obtain this from restricting the variation sequence to the regular loci, as you may do in the stratified setting, and then this falls into your hand. And you may say, okay, why do I care about a single stratum? I want to have the whole singularity. But what you can do is you can cut down so far that, sorry for going back and forth, but I remember it's on this slide. If you cut down so far that these are smooth, then they coincide with the regular loci, right? And then you really get the whole space. And what this means is that as soon as the codimension I is sufficiently big so that these spaces are smooth, then you have a short exact sequence where here you have the truncated cohomology of the regular locus of the model singularity. Truncated meaning only those parts in degree less than d, they embed into your space, into the cohomology of your complex link of codimension I. And then you have some quotient q. And what you know is that this quotient q is concentrated in cohomological degree d, where d is the dimension of, or is supposed to be the dimension of this complex link. Okay, yes, that was that. So, where do we go with this? For the links of the generic determinantal varieties, well, I already showed you the formula for the cohomology of the stratum, or of the different strata in the rank stratification. And when you put all this together, then you see the following. Here, for cohomology with coefficients in a field, let's say, to have a simpler statement, the cohomology of the complex links of higher codimension of these generic determinantal varieties, they read like this. You have a contribution of this Grassmannian part with this truncation here, right? So you take the cohomology of the Grassmannian, you cut off in some degree d, determined by the dimension of your complex links. And then here you have some remainder term, which is again concentrated only in degree d. And the number nu, the rank of this part, still has to be determined. Okay, this is what I just said. And this is now another thing. You may want to know this number nu. And one way to know it is, okay, if you know the Euler characteristic of your complex link, then you can just subtract the terms introduced by the Grassmannians, and the remainder must be your nu, or your nu. And there are several ways to obtain these Euler characteristics. People are usually good at doing this, and one way is to write it as an alternating sum of polar multiplicities, right? So I call E, M, N, R, K the polar multiplicities of the generic determinantal varieties. And I want to give you this because, as a matter of fact, these polar multiplicities can be effectively computed. This is another thing I do in my preprint, but I'm afraid I cannot claim much originality to the subject. So this is one formula I give. I should say Xiping Shang has also developed methods some time before to compute these polar multiplicities. And you should also maybe look at his papers. He's doing something more general. I've tried for some time to find closed formulas for these polar multiplicities. So this is a formula you can put in the computer and it will give you numbers. For every set of number M, N, R, K that you put in, it will give you a number. It will spit out a number for you. But I found myself unable to prove a closed formula for this. So if you find one, I think that should be nice. Let's go back to the characteristic cohomology thing. we saw what happens for the complex links. And now let's consider again, or the complex links of higher codimension. And now let's consider the general setting of a determinantal singularity, right? So here's your determinantal singularity. It's defined by some matrix A. Then you have a determinantal smoothing, or this is, I should say, this is a condition in this theorem. It should be a determinantal singularity with a determinantal smoothing. Right? It's the condition on moving the image away from the from the singular locus of the model singularity. And if all this holds, then here this truncated cohomology of the Grassmannian sits in the cohomology of this determinantal smoothing. And the quotient is concentrated in cohomological degree D. Moreover, this cohomology of the Grassmannian that's embedded in there, it's really the characteristic classes of a specific vector bundle, namely the vector bundle which is presented by the perturbed matrix A. Right? And a particular consequence for isolated Cohen-Macaulay codimension 2 threefold singularities, which is a very specific topic, but it used to be the topic of my thesis years ago, and it was not completely solved yet, what the cohomology of these singularities is. So now we have the full result. Whenever you have an isolated Cohen-Macaulay codimension 2 singularity of dimension 3, then you have can pass to its smoothing M, and the second cohomology group of this smoothing is free of rank 1 and generated by the Chern class of the canonical bundle. This is a particular case of the theorem I showed you before. So I have some minutes left. So let's get back to the question by Jim Damon, and we just recall the question here. Jim Damon was studying mostly the hypersurface case, he put some emphasis on the hypersurface case, and he found this direct sum decomposition, the cohomology of the Milnor fiber of your singularity of type Y splits as characteristic cohomology plus some free term which is concentrated in degree equal to the dimension of your Milnor fiber, and the question was, how must this be modified for general singularities of a given type? So my suggestion for isolated determinantal singularities which do admit a determinantal smoothing, so deforming the matrix must induce smoothing of your singularity. I say the cohomology of the determinantal Milnor fiber here, it is isomorphic to the pullback of the cohomology of the stratum plus some term Q, which is the Q that you saw earlier from the complex link. And then some free term, some additional free term of rank lambda, with lambda from this Bouquet decomposition, which goes back to the work of Mihai Tibar. So, yes, let me pause here for a moment. Something that I did not write is where does this come from? What's behind this is the Bouquet decomposition, which was here the following. This MAS is homotopy equivalent to the appropriate complex link of higher codimension, MN, and then S, and here the codimension MN minus P. And then here this wedge I equal 1 to lambda, and here the spheres SD, with D the the dimension of your singularity. And this part is coming from here, and the other part here is coming from that. So I think now my time's used up, and this is also where I wanted to stop. So here's the short bibliography, and thank you very much for your attention. That's it. Thank you very much.